Okay, cool. Welcome to Lecture 11. So, I asked you all what were some interesting topics for us to cover in the last couple of lectures that we have left. And the most popular option was a deeper dive on GANs. We talked already a little bit about GANs previously in the unsupervised set of lectures, but GANs, also known as generative adversarial networks, are quite a deep topic. And so this lecture is really going to be about kind of GANs. What are they? What are sort of the pros and cons of them? What are some of their issues? How do they work? And how things have been improved over the last 6 7 years, which is when in around 2014 they came to prominent, like they were introduced, and they've really come into prominence as one of the better approaches for generative modeling with very very high fidelity and diverse. Well, we'll talk about this more as we go through the lecture samples. And so there's a lot to cover in this lecture. I put together the slides and very quickly got to a very large number of slides. And so, on the one hand, I do want to go deep on some of the technical aspects of GANs. I won't talk too much about implementation, but I do want to kind of cover the math a little bit and make sure that you can develop an intuition for these as we go through them, because it's really going to be rapid fire. But what's really nice about GANs is that they're quite intuitive as compared to a lot of the other machine learning, things that we've been talking about. So let's kind of dive into it and let's get going. So originally, GANs were introduced by Ian Goodfellow et al. In a pretty exciting paper called Generative Adversarial Networks. This was in 2014, and the idea actually apparently came to Goodfellow like he was like drinking with his buddies, and he was a little bit inebriated, and he was like, "I bet this would work," and his friends were like, "Ah, what are you talking about?" And so he actually went home and tried it and found out that yes, indeed, this was a effective strategy, and it's just kind of gone crazy from there. The general idea of a GAN is you've got actually two machine learning networks that are acting in an adversarial fashion, meaning one is sort of pulling while the other one is pushing kind of situation. And basically the two building blocks of a GAN involve a generator. So this generator is a machine learning network, a neural network that is outputting samples, it's outputting data, and then a discriminator that is trying to determine whether data provided to it is from a data distribution or p data, the real distribution of data, or it's fake. So it's essentially this game, also known as a minimax game, as we'll talk about the loss function that you're optimizing here, where the generator is in essence trying to fool the discriminator. And so you're training both of these networks sort of not jointly here, because jointly means that they're being trained on the same loss function. Here you're actually alternating and simultaneously training these two networks. So the loss function is essentially just the binary cross entropy of the result of the discriminator. So the idea, this top equation here, is the loss function for the discriminator. Right here, what we're doing is we're saying the discriminator's loss. We're going to well, actually, this is the whole thing. But in the case of the discriminator, right, the discriminator is going to try to minimize the situations when it's wrong, and maximize minimize the situations that it's wrong, and maximize the situations that it's correct. So that's the idea here, is that given fake data, the discriminator wants to provide an output of 0, and in given real data, the discriminator wants to give you an output of 1. That's the goal of the discriminator, and that's essentially the loss function. On the other hand, the generator is trying to fool the discriminator, and so in this case, the generator's loss function is essentially just the output of the generator, and it's trying to make sure that the output of the discriminator is now going to be close to 1 for the data that it provides it. If you read through the paper, and I also recommend checking out Lillian Wang, I know I've mentioned her blog post a lot, but this is a really good one. Lillian Wang's blog post about GANs. And we'll talk about all the different things in that blog post in this lecture. But if you read the paper, what we find is the optimal generator and optimal discriminator ultimately results in us minimizing this divergence, the Jensen-Shannon divergence, which we'll talk a little bit about throughout this lecture. But at its core, the idea is that we have this sort of binary cross-entropy loss, essentially logistic regression of the discriminator. And what we can do is we can take the signal from the discriminator of whether it's right or wrong and propagate that to the generator while also training the discriminator on that as well. And so you can kind of see that this sort of joint loss formulation here is minimizing for the generator while maximizing for the discriminator this loss function of the expected value of the discriminator against real data, so x drawn from the real distribution, plus the expected value of log 1 minus the discriminator operated on the fake data. And the reason it's 1 minus is because here what we want to do is we want to make sure that the discriminator is correctly determining that the fake data, or g of z, and z is actually just a value drawn from some random distribution, right? So this generator being provided with this z value outputs some data, and that being provided to the discriminator wants to be able to determine that actually that's fake. And so it outputs 0, and so that's why 1 minus the discriminator is what we want to optimize for here in the case of the discriminator, because 1 minus 0 is 1, right? Whereas log 1 minus 1 would be log 0, which is negative infinity. So that's why we're maximizing for the discriminator. And you can kind of equivalently see how you would do this for the generator, where the generator, you wouldn't have any real data, so this first term just goes away, but instead you're trying to minimize this loss, meaning you're trying to go into the negative, you're trying to fool it. So in the case of the generator, right, we want d of g of z to be close to 1 because we're trying to minimize that. So you can kind of see these two networks are being trained in different directions. And ultimately what this results in is this sort of divergence between the real distribution and the fake distribution, and trying to minimize that distribution. So to minimize that distance between the two distributions. And we'll talk more about this throughout this. But you can kind of see this is just the binary cross entropy loss, which we've seen before in logistic regression. So let's talk a little bit about the binary cross entropy loss. What a GAN is doing is it's actually trying to achieve this Nash equilibrium between the generator and the discriminator. If you get to a perfect equilibrium, you can kind of imagine that the discriminator has a 50-50 chance of determining whether fake data is real or not. And that's sort of the Nash equilibrium. This is what's also known as a minimax game, where one agent is trying to maximize a value, whereas another one is trying to minimize it. And the original SGAN, or standard GAN, used this binary cross entropy loss to accomplish this. You can see this sort of again on the right. This is the actual original GAN algorithm. I'm not going to go through it too much yet, but the problem with binary cross entropy loss, which is just this y times the log of the output plus and so on, 1 minus y times the log of 1 minus the output. The issue with that is that it's got some issues for this, and we'll talk about that shortly. But to just talk about the standard GAN, original paper, one of the things that's sort of notable here is that it largely worked on MNIST data, but it was based on like these MLPs and these fully connected layers, and it wasn't doing anything too fancy. And the results were very, very good. You can kind of see here that's like a kind of representative result down here in this diagram. And the results were quite good, but they weren't like great. And as we'll talk about later in the progress of GANs, you'll see that the original GAN paper, while it was like, wow, this is amazing, they weren't necessarily fooling anybody, right? This was a very compelling, interesting approach, and definitely state of the art at the time for generative modeling. But it was still early on, and some of the issues have come up, like that around the BCE loss in particular, which we'll talk about in a minute. But because this was kind of like a flat architecture, the next thing that people tried to kind of do, not next, it wasn't immediate, but in 2016, Alec Radford published, along with his co-authors the DC GAN. So this essentially is just taking that original architecture, that BCE loss. Not very much has changed here, except instead of a fully connected set of layers, we're now using convolutional neural networks. So the generator is actually upsampling by way of these transposed convolutions, as we've talked about, going from the latent space, this 10-dimensional Z in the case of the DC GAN, up into a 64 by 64 image, RGB image. And then the discriminator kind of equivalently would downsample that using just strided convolutions, as we've seen. And the output of that would just be running through a sigmoid. And again, you're just going through the same algorithm. Actually, the algorithm itself is the same. It's just the architecture of these networks has changed. And you can kind of see just like this massive jump. Now we can do color, we can do larger pictures, right? MNIST is like 28 by 28. Now we're talking about 64 by 64. This technique actually also works for larger resolutions. But one notable thing here is if you're going to play with DC GAN, you'll notice that the transposed convolution actually has this checkerboard artifact. There's a really great article. If you go to this link here, I recommend you check it out and understand what's problematic. But because we're doing this strided type of deconvolution, certain pixels are getting way more attention than other pixels, and you get these sort of kind of artifacts that you can kind of see here. So it's not so much a problem. If you train this thing for long enough, eventually the model will figure it out. But as we'll see throughout this lecture, the problems with GANs is instability, length of training, these kinds of things. And so this is actually one of the things that has been really drastically improved on. And you can kind of see the samples coming out of DC GAN are like getting better, but they're not like great. They're still kind of like nightmare fuel, right? Like this kind of looks like I don't know, like a bee and kind of a dog. And I mean, the samples are really impressive, right? They're clearly pictures of something. And they're clearly pictures that are very similar to pictures in our this is from SciFar, which is a data set of 60,000 images with about 10 classes. It's a small, they're like 32 by 32 and 64 by 64. So it's a very valuable data set. But you can kind of see the images are like not real. Even in the examples that they provided here in the close-up, you can look at the images that they're sampling into, and it's like, that's not like a real picture of anything. So still, we've got some improvements to make, but already we're state-of-the-art in terms of generative modeling, in particular for images. So let's start to talk a little bit about one of the issues with the GAN BCE loss, and that's with vanishing gradients. Consider a GAN where the discriminator is perfect, right? It knows, it's trained, it knows what real images look like, it knows what fake images look like, but our generator now is no good, right? Our generator is just starting to train. And what's going to happen here is that the discriminator is going to be so good that the generator is never going to get much signal. So you can see the top is the gradient for the discriminator, right? But the bottom is the gradient for the generator. And the generator is only dependent on gradient signal from the discriminator. So if the discriminator is constantly saying that your data is fake, this value, log 1 minus 0, is going to be 0. And that's no good, right? That's essentially a zero gradient. And so we actually have this problem with vanishing gradients using the binary cross-entropy loss for GANs. And this is sort of like the equivalent example here of, after you can kind of see this, the gradient with the generator with the original loss after 25 epochs, right? You can kind of see the gradient starts to lose signal as the discriminator starts to get too good. Keep in mind here, right, this is something often is spoken about GANs, right? When you're starting to train the GAN, the GAN networks, both networks are not trained, right? And so the generator is generating samples, random samples, but the discriminator is also kind of like doesn't know what real or fake looks like either, right? It's learning only from this signal. But in the case of the discriminator, you've got these two sources of signal, like you're averaging them, and so overall magnitude is reduced, and perhaps the way and the dynamics of training you can kind of compensate. But the generator only has one source, right? And it has to go through these two networks as well. So often what you'll see throughout the sort of GAN literature as we're going to go through it is that what we're trying to do is actually sort of disable the discriminator a little. Like we can't have the discriminator be so much worse in the same way that we have diminishing gradients in when the discriminator is really good. The same can happen if our generator is too good. If our generator gets too far off and is generating images that are too amazing, or as we'll talk about in the next slide, about the same image, but that particular image is great, but it doesn't produce anything else, and so the discriminator is saying that looks good too, but it's like the same thing, or it's not very good. Then similarly, the discriminator doesn't get good either. So in either kind of side of the spectrum, you have this problem where the two networks may, if one of them exceeds the other too far, you get this sort of state of instability, and you no longer have a good you no longer have good training dynamics, and your overall samples are just going to look the same, right? Your generator is just not going to get improve or change whatsoever, which is not what we're after. So yeah, the other issue that we have with GANs is what's called mode collapse. And I kind of mentioned this just a second ago, right? If the generator outputs just one image, and it's a perfect image, but nothing else, right? It's just that one image, it only outputs one thing. That thing is perfect. The discriminator can't detect the difference between that and the real data. The discriminator is going to respond with, yes, that's correct, and your generator is not going to evolve or improve, and your discriminator is not going to evolve or improve either, which is problematic. Unless maybe it improves on the real data and gets better at determining that real data looks real. So one of the kind of ways to analyze this is by way of the Jensen-Shannon divergence, right? If you kind of break this down, GAN is trying to minimize this divergence in the Jensen-Shannon divergence, and the explicit definition of the KL divergence is here, where it's the JSD divergence is here, where it's actually the sum of a KL divergence between P data and this average distribution plus KL of the P fake and this average distribution. You kind of break this open, especially on the right side, and you see that you actually have what's called the reverse KL divergence between the generated data and the data the real data. And the problem with reverse KL is that it tends to be mode seeking. And what that means is it tries to find a mode, and you can kind of see this exemplified in this diagram here. So the forward KL divergence will try to be mean seeking. It'll try to cover the entire distribution, even if it's sort of an average and sort of fuzzy. This is what we saw with variational autoencoders, which use the forward KL divergence, and that results in very good coverage of your distribution, but not very good contour mapping, right? If you have a really sort of bumpy distribution, the mode, the mean is just going to sort of collapse those things into an average, into a sort of like everything's good if it's but it's not quite the best. The mode seeking is a little bit the opposite, right? Where instead of trying to cover the entire distribution, what we're doing is we're actually trying to find the place where we can maximize this. And this comes down to the fact that in the reverse KL divergence, what we have is we have this P data. We have this the fake distribution in the denominator. And your fake distribution in the denominator is not the best news, because if you have 0, then you're dividing by 0, and that's not a happy situation, right? And so what you end up having is a situation where you're trying to if you're trying to minimize this thing, then you're going to try to have a non-zero distribution everywhere, but you're going to maximize by dividing that in these modes. I'm not describing this particularly well, but the math sort of ends up kind of doing this for you, right? Because the equivalent is if you have p data in the forward distribution, now you're dividing by p data in places, and to minimize that, what you need to do is the generator essentially has to go to 0, to the average. Whereas here, if we want to do is we want to sort of find places where the two overlap maximally. So I might not be describing this very well. I always get kind of mixed up between the forward and the reverse KL. But to wrap it up in a bow here, the difference is that the reverse KL is mode seeking. That's in this sort of JSD divergence, and because of that, often what we see is this mode collapse where you end up really focusing on a particular part of the distribution and not the whole thing. This is actually demonstrated here before we go into LS-GAN. In the bottom right, in the LS-GAN paper, you can kind of see in the regular GAN here, right, as we go through iterations of training the GAN, you can see the target distribution is here on the right. It's the sort of equidistant circle, and we're learning this distribution that ultimately collapses down into a particular mode of that distribution, whereas LS-GAN is able to actually cover all of the modes more equivalently. So LS-GAN came out and they basically said, look, like the BCE loss is no good. If we utilize the least squares loss, it's much better, right? These diagrams from the paper are quite that demonstrate this quite well. On the left, this is the one side of the cross entropy function, meaning you have two sides, right? You have the log of x and then log of 1 minus x, right? So this is just one side of that binary cross entropy loss, but you can see that it sort of goes up to it just goes up forever, and then eventually flattens out. So you have this diminishing gradient thing. But with the least squares loss, you actually have this parabola, right? And so at no point except at this optimum do you have a zero gradient, right? That's a good thing. We kind of want our loss functions to look like this mean squared error, because we always have a direction to go. We're always climbing a hill or going down into a valley, and that's much easier to do than, for example, this binary cross entropy loss, which has this problem of these two ends that kind of go up and down, but they're not related. So you can actually get stuck in this sort of flat area, especially in the case of GANs, because in the GAN, right, one side of the cross entropy loss is dependent only on the discriminator and the real data, and the other side is dependent on the discriminator and the generator, right? And so you have this asymmetry between the two terms, which can mean that both terms are stuck in this flat part, and you're not making any progress. Whereas if you use the MSE, you're always making progress in some way on both sides. And so you can see the reformulation of the LS-GAN loss function. So here, instead of doing the log and blah, 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 we're taking the discriminator, we're subtracting from it a value of some kind, and taking to the power of 2. Generally, by the way, this is just 1. Like the B and the A values are just set to 1, and C as well. But you can choose whatever value you want. It's sort of your belief value, but that's up to you. Generally, I've seen just 1 being effective, and you can just see this works quite well. Notably, CycleGAN adopts this MSE loss, so you'll actually see in literature a lot of GAN still use the BCE loss because it's fine. You just have to kind of parameterize, like you have to tune parameters and sort of nudge it, and that's not so hard. It's just annoying. Very few people actually care about the stability of the GAN as long as it's working, and if it's not working, then they just poke around until they get it to work. But if you're interested in the theory and getting these really robust systems working, because keep in mind, this only matters in training, right? Once you train your generator and you're outputting really good samples, at test time, at inference, you're not using the discriminator at all. You're just using the generator. And so that's something to kind of take note of, is a lot of these optimizations and improvements have really to do only with training and not with inference. But inference is important here because if you don't train your network well, then you're not going to have a good generator, and then you're not going to be producing good samples. So, you kind of have to do all of it. But anyways, LS-GAN introduces the MSE, the mean squares error loss, and it was a nice step forward. Oop. Cool. So this is more of an honorable mention because I don't think I've seen this very much, but at the same time, it's very interesting and a good idea to kind of explore. So, and we'll also kind of hit on a similar idea in this lecture as we go through it. So InfoGAN tries to maximize the mutual information, and so this is the intuition here. It's very interesting, right? So we haven't talked a little bit, actually we haven't talked sufficiently about the generator, but the way that the generator works is you have this Z value, this latent is essentially drawn from some type of distribution. Often we use like a normal Gaussian or a uniform, whatever. Use your favorite distribution of choice. And we take this value, it's going to be some dimensional a noise vector, some dimensional random vector, and we're going to plug it into our generator, and then the generator operates on that, and then it outputs a sample, and then that sample is plugged into our discriminator. The discriminator determines whether or not that sample looks like the real data distribution or not. So cool. So one thing that's interesting, an interesting idea that they tried to use here is that basically, what if the latent has some information about the sample being produced? When you provide one value, it'll produce this sample. If you provide a different value, it produces a different sample. So the Z, this random noise, isn't so random. It's ultimately some kind of representation of this sample, right? If we could, in theory, go backwards in the generator, going from the target, from the image to the latent, that would be some way to classify. There's actually a similar GAN, I don't talk about it in this lecture, called bidirectional GAN or BiGAN, that literally does this. It jointly trains an encoder to go back and forth so that you can sort of reverse the mapping between image to latent space and vice versa. So the idea with mutual information maximization for GANs is that the input to our generator is now going to be a content latent, some kind of value that is not so noisy. It's not random. It's sort of our latent, our new latent. We're drawing it from some distribution, and then we're going to plug in another. We're going to concatenate that with noise. Random noise, incompressible noise. So this is actually noise, not a sample drawn from a distribution, but just random noise. And then we're going to run that through our generator, and then the output now should have some information about it related to that original C value. And so what we're going to do now is we're going to run that through the discriminator like we've been doing so far, but also through a separate auxiliary network called Q that's going to try to extract this C. We're going to learn this network as well. And then this output from this network, what we're going to do is we're going to essentially create a cross entropy mapping between that C and the C that we plugged in. So that's how we're going to learn Q. And then we're going to maximize this mutual information that we're going to approximate between the output GZ, the generated image, and this value C. So what we're trying to do here is we're actually trying to maximize the information between this C, this content encoding, and the output of the generator. Now, the problem with mutual information is a way to sort of determine how much entropy is shared between two random distributions. You can see the definition here. The mutual information between x and y is equivalent to the entropy of x minus the entropy of x given y, and equivalently the kind of the alternative formation. And so the problem is we need to have this entropy of C given. It's very intractable. But we can approximate this by way of the elbow, the evidence lower bound objective, like we do in a VAE, which essentially just means that we're trying to minimize the KL divergence between this Q network and our generator network. And so this kind of all distills down into this loss function where we're trying to maximize this expected value of this Q network. So if this is a little bit mathy, don't worry about it. It's essentially like we're basically setting up a VAE between the output of this G, the generator, and the content encoding. And what's really fun about that is now you can kind of plug this into the discriminator, and just this improves the training, and it improves the stability, because what we're making sure is that these values coming out of the generator have some better like disentanglement on the input on this C thing, and the Z is also another way to kind of permute our values. So it's quite cool. Another note is the Q network and the D network and the discriminative network actually tend to be the same except for the last layers. So you don't actually need two different networks. You can do this on the same network, except the output. You have different sort of heads on the networks. So this is a fun experiment to run. Following the paper, it ends up being really interesting. And so InfoGAN was sort of one of the first approaches to really treating the latent, like looking at the latent space and saying, hey, the latent shouldn't just be random. Maybe we should do something about this and sort of link it to the generator's output. And by maximizing this mutual information between the generator output and this latent input, we were able to ensure that we don't get mode collapse and things like that, because we're really we're really encouraging this sort of maximization of the information through the generator. So yeah. Cool. The next big topic in GANs starts to get into what are called integral probability measures. And so I'm not going to go too deeply into the Earth mover's distance. I encourage you all to kind of go look into it a little bit more. But so we've been talking about reducing the divergence between these two distributions using the KL divergence or the Jensen-Shannon divergence. But as we've seen, that both of these have really unpleasing sort of situations where you're dividing one distribution by another distribution. Often one of these distributions is a learned distribution, which has zeros in certain places, and we can have very unstable sort of situations such as mode collapse and just general instability. And so the Earth mover distance kind of goes back into what's called optimal transport theory. And this sort of is literally like, imagine you have two piles of earth, like dirt. What is the kind of minimum amount of work that would need to be done to move the dirt from one to the other? How would you sort of convert the two distributions into each other, and by literally displacing the dirt from one, putting it into the other one? That is the Earth mover's distance, or also known as the Wasserstein distance. And this is a very difficult thing to calculate. The definition explicitly of the Earth mover distance is down here in the bottom, where this gamma component is essentially every pairwise joint probability distribution of moving dirt from whatever. It's like basically the minimum cost, like the one that requires the minimum amount of effort. Given these two things, then you subtract the expected value of these two of this. It's almost like it's very intractable. It's basically like saying, let's try out every possible combination of transports and then choose the one that reduces the absolute difference between them. It's this x minus y, because x minus y is drawn from gamma, and x minus y being the amount that's moved from one into the other. We want to reduce that as much as possible. So it's not exactly tractable, but then we have the Kantarovich-Rubinstein duality to the rescue. And what the Kantarovich-Rubinstein duality showed is that actually the Wasserstein distance is equivalent to this formulation, where we have a function and the expected value difference of this function, given that this function is what's called K-Lipschitz. And so K-Lipschitz, I know these are all wacky terms, and don't worry, at the end of this is a nice little cookie that makes this all very simple, and you don't have to remember all this math. But K-Lipschitz just ensures that a particular function does not exceed in its norm the gradient of a particular value. And you can kind of see this in this image. This is drawn from the Wikipedia article. You basically, at any point in the function, you draw a line with the slope equal to the k value of the Lipschitz. So if it's 1, it's just x equals y at that point. And you want to make sure that the function always exists within those regions that are being drawn. So if the function intersects one of those lines, then it's not K-Lipschitz if you sweep that all the way across. Formally, this is defined as essentially the rise over run of any particular point in the function divided by any other x point, and this has to be less than k. So we're just doing this literally making sure that at no point does this function have a slope greater than this K-Lipschitz value. So this sounds like all cool and everything, but like how do you do this? Like how do you have a function that is K-Lipschitz? I don't know. I mean, we can't. How do we enforce this kind of thing? So, yada blah blah blah. We clip the weights. So this is kind of the fun part about the W GAN, or also known as the Wasserstein GAN. It's literally a normal GAN, but then all we do is we clip the weights of the discriminator to be within negative C to C, and C is just a parameter you get to choose. Often it can be 1 or 10, or it doesn't really matter. But what this means is that the discriminator never exceeds the K-Lipschitz constraint that we need to be able to do this Wasserstein distance. And that means that now we can just take this expected value for the fake data of the discriminator and subtract it from the expected value of the discriminator against the generated value. And so our loss function is much simpler, right? You can kind of see here in line 5, right? It's just we're taking this f of w, this is just our discriminator, and we're running it on the real data, and we're subtracting that from this discriminator run on our fake data. And the only real thing we have to make sure is that the w, the weights of the discriminator, never exceed c and never go below a value of negative c. So it's kind of underwhelming. The paper is quite mathy. I recommend you read it. It's a lot of fun. But at the end, it's like, well, this is a good approximation. So we need some more stability, because apparently clipping the weights from negative C to C is not always the best idea and can cause a lot of instabilities, and it's relatively hacky. It did improve things substantially, but it didn't do the best. And so actually the gradient penalty, or the Wasserstein-GAN gradient penalty, introduced this idea of, instead of clipping the weights arbitrarily, what we'll do is we'll penalize the discriminator from having a gradient greater than our K-Lipschitz constraint, which is usually just 1, right? Because we're trying to maintain K-Lipschitz of 1. And so the way that we do that is this sort of term you can kind of see in line 7, this lambda times the gradient of the discriminator times run on x hat. And let me talk about x hat in just a minute. And then the L2 norm of that minus 1 squared. So this is basically just saying, if our gradient exceeds 1, then take that to the power of 2 and multiply it by this lambda. Often lambda is equal to like 10 or something like that. So one note, x hat, getting this to work is actually a little bit tricky, because what do? You run it on the real data or the fake data. So actually what ends up happening, and is done in practice, is you interpolate this. So this x hat is an interpolation between the real and the fake data, and you literally just sort of take epsilon, some random value between 0 and 1, and you multiply the fake data by epsilon, and then you multiply the real data by 1 minus epsilon, and you add them, and then you get x hat. Yeah, it's just kind of a nitpicky thing. Otherwise, this sort of, what does that mean? What does that gradient mean? Because this actually involves another backprop pass. Because you have to calculate in the loss function this gradient. Because remember, in machine learning, right, we calculate the loss function, and that gives us then our gradient to update our parameters. So here we actually have to get the gradient of this network for the loss function. So just a note there. You do have to run this separately. So getting gradient penalty to work is actually a lot harder than just clipping the weights, but you can kind of see in theory it's much more stable and a little bit more intuitive of like why this works, because we're not just clipping it arbitrarily. We're basically encouraging, through the loss function, through the objective, we're encouraging the discriminator network not to have a gradient greater than 1. So yeah. This one I don't actually see in practice as much, but spectral normalization GAN essentially came along to the same problem of K-Lipschitzness in the discriminator and said, well, like, why don't we just solve it for real? And so what it does is it says we're going to look at every layer in a network as the sort of set of composable functions, and if each one of those composable functions maintains a K-Lipschitz constant of a certain value, then the whole thing also has that. And they leverage this idea, which requires them to sort of determine what the largest singular value of the weight matrix is, and then divide by that. So basically, they're dividing by the normalization, the norm of the largest singular value. This is like basically in the context of singular value decomposition, like in linear algebra, where you take a matrix and you sort of break it down into its respective components in SVD. Now, you can imagine SVD is not cheap to do, especially at every training step, and so they actually utilize this idea of power iteration, which is a really great way to approximate the singular value, which they run through in this algorithm here, which involves essentially pulling a random vector from randomly, and then applying this power iteration method to it, which over time gets you closer and closer and closer to the actual singular value. And they've actually shown that because you do this at every training step, and every time you do this, you're getting closer and closer to the actual singular value, and the weights aren't changing all that much. This actually is very, very effective, requires almost no compute, additional overhead, and within just 2 or 3 iterations gets you quite close to a K-Lipschitz layer. So this is another approach. It's not, I don't see this getting used as often, but if you want to try it, they actually have, PyTorch actually has this as just a utility that's been implemented, and you can go and just throw it into your model and see what happens. This is a special mention. This is a recent paper I read. Again, I haven't really seen it used anywhere, but it's an interesting idea that tries to generalize this idea of integral probability measures in GANs in general, and so applies it with an SGAN, but without actually using any of these ideas. And the way that she does it is by way of, instead of running the sigmoid, the discriminator, on the value of the real and the fake data, instead you run your data through the real and fake. You subtract that, so you can get a relative score, a sort of differential score, and then you run the sigmoid on top of that. And this idea is quite unique, because what it's saying is that the discriminator knows that you're providing it with fake data and real data, right? It sort of knows that some samples are going to be real and some samples are going to be fake. And not using this information is just a waste, right? It's almost like playing a game with your friend, and you're giving them a bunch of words that are real words and some words are fake words that you made up, and you're trying to convince them that some words are fake and some words are not. And your friend knows that at least a few words are going to be fake, right? And that knowledge makes them perhaps say certain words are fake when they're real, and certain words are real when they're fake. And that sort of relationship between real and fake is an interesting idea. And so she kind of came along and said, well, if we run this relative mapping, like this relative difference before we run it through the final layer of the discriminator, we get much better results. And actually, in reality, like in her experiments, she got 4x faster convergence. So you need 4x less compute to get to state-of-the-art results with this approach in training. And you can see what's really fun about this is there's no earth mover, there's no spectral norm, there's no math. It's just this idea. Actually, the paper itself is quite math heavy, but the idea here is quite eloquent. And so this is a fun special mention. I haven't seen this used too much, but it's something that seems very promising. So let's move into a little bit of kind of state of the art and less theory and more stuff that people are doing. So GANs have improved like rapidly. So this is a picture from Ian Goodfellow's tweet about it just a few years ago, and it's actually improved even further since here. But you can see in 2014, the original GAN paper, I mean, it looks kind of grainy. Maybe it looks like a picture from like the 1910 or something like that. But like then we're getting slightly better pictures that you can kind of tell that they're generated. I mean, they look quite real, and you might be like, oh, that's a real person. But the images the quality is quite low. But then we're getting into like StyleGAN and StyleGAN 2, and these images are it looks like a real person, but these people don't exist. These are actually outputs of a GAN network. And so, this is usually the part people start talking about the ethics of GANs. I'm going to leave that to you. Don't be jerks. Like, you can definitely use this for bad. Hopefully, in the context of this course, we're talking about games and game development and enabling creative uses for these technologies. So yeah, you can definitely abuse these technologies. You can definitely create fake profile pictures and all this stuff, and people are doing that, unfortunately. So just food for thought. Use this wisely. So the first kind of big result was StyleGAN. StyleGAN kind of goes from this traditional. It's all in the generator, by the way. So the StyleGAN's focus is really how do we generate maximal fidelity samples. The discriminator is essentially the same as SGAN, but the generator is really where they focused. So instead of going from this latent space drawn from a random thing and just kind of running it through a bunch of different layers, first they take this and they map it to a W space, or what's called like a style space. And that style is then affine applied to these adaptive instance normalization layers. And what you're kind of doing is you're modulating each layer through this thing. Another thing that StyleGAN used was what's called progressive growing. And so it starts off with generating like 4x4 images, and the discriminator equivalently is judging 4x4 images, and slowly grows from 4x4 to 8x8 to 16x16 and so forth until it gets to its target resolution. So that's also something. You can kind of see this additional noise, the stochasticity that's being injected into the network. And what's really cool is this is sort of going from like coarse, low-level features like just sort of general color and contour to higher and higher fidelity and more intricate detail. And so the noise, for example, up here might affect like skin color or the background. And down here, as you get kind of into the higher resolution, the noise is going to affect like the position of hair or wrinkles and things like that. Much more fine-tuned stuff. So StyleGAN is really interesting because it leverages this adaptive instance normalization modulation of this latent into this mapping network, and we're starting to get a bit more sophisticated about how we're generating samples. Quickly, I should add, StyleGAN 2 came along and fixed a lot of the problems that StyleGAN 1 had. There were certain situations where the instance normalization was resulting in these sort of blob artifacts where a lot of signal was getting kind of like lumped in there, because then the generator was able to kind of move signal around using this thing. And so what they did is they split up this original StyleGAN. As you can see, you're modulating, you're upsampling, and so on. They split this up into a way where the noise is added separately and outside of this whole thing, and we're actually demodulating the weights themselves. So instead of modulating the data, the signal, we're actually modulating the weights and applying these statistics to the weights, which resulted in much better results, and largely about cleaning up these artifacts. So, I guess there was an animation there. Sorry about that. But yeah, but you can see these samples. These are from StyleGAN 2, and they're like phenomenal. They look really amazingly real. And so StyleGAN 2, a relatively small change to the first StyleGAN, but got rid of a lot of these sort of nasty artifacts that, even though you would kind of need a trained eye to find, were not desirable. The next kind of notable GAN is the Big GAN, and Big GAN essentially just sort of did this at scale. They used ResNets, they scaled up to very deep networks and larger resolutions and a shit ton of compute. And this is actually not that much different than the DC GAN we talked about earlier, except we're using res blocks and things like that to allow us to have much, much deeper networks. And you can see we get some really high quality samples, but sometimes we get a little bit of nightmare fuel, like this sort of tennis ball dog thing. So you can kind of see it doesn't do. These are still generative networks that are, kind of not aware of what they're rendering. They're just sort of trying to replicate a set of input data. Something that big GANs did that I think is notable is what's called the truncation trick. So you're taking this z value and you're drawing it from some random distribution. If you're doing a Gaussian, like a normal distribution, you have this bell curve, right? And just like in reality, like a bell curve, in this case, you have these very unlikely values that you can be drawing from. So you can kind of imagine there's some wacky taco dog things over here, and you've got some other things over here that you don't want. There may be valid samples in your distribution, but they don't make any sense. And so the truncation trick is really simple, where you just truncate. So if you randomly sample, and if you sample something outside of, like, say 2 sigma deviation, you throw it away and you just sample again. So you only maybe you train on all of the samples on the full distribution, but when you're sampling, you truncate that. So that's something to kind of think about. So this is a moving target. GANs are constantly improving. I think there's like a new paper from the Style GAN authors. I forget. I haven't read. I can't keep up with all of them. Some of these papers are relatively recent, by the way. I think Style GAN 2 just came out a year or two ago. So this is a very active area of research and something that is a very exciting place to be in unsupervised learning. Because again, remember, in almost all of the cases here, we're talking about data with no labels, right? We're just giving it a bunch of images and it kind of figures out what those images look like and then how to generate new ones. But what if we want to have some labeled data, right? What if we want to output specific things? If we know about our data set, right? What if we wanted to produce images that are specific to a particular class? And so not much, very quickly after the original GAN paper, the conditional GAN paper came out, which talked about, well, if you concatenate a class to your input z, this is kind of similar to what we saw with InfoGAN, right? But if we know that, if we have a deterministic value there, and we say, well, I have 10 different digits in this data set, I'm going to concatenate the digit number, right? And then I'm also going to pass that value to concatenate that as input to the discriminator. So now the discriminator knows, okay, this is supposed to be a 7, and this looks like a 7. So now the discriminator can tell me, even though I gave it a very realistic looking 4, it can tell me, actually, this 4 does not look like a 7. You asked me for a 7. This does not look good. So this is a relatively simple idea, but it resulted in very, very cool results where now if we have a multimodal distribution, and remember, this is important for GANs because GANs have this issue of mode collapse. Well, if we kind of get ahead of the problem by saying, well, we're going to take a multimodal distribution and we're going to turn it into a bunch of unimodal distributions, then we don't really need to have this concern. And so not only did it get better results and better samples, but also now you can be targeted. You can say, I want to do this. But now you need to have labels for this data, which is maybe not always available. So it's a very cool thing. So this led to, I think, one of the more exciting aspects of GANs, which is what's called image-to-image translation. So instead of talking about a single class, what if we have data associated with our entire image? And so this paper came out called Pix2Pix, and Pix2Pix essentially does exactly that, where instead of concatenating to our input z a particular class, we're actually using an entire image. And in some cases, we don't even need the z. We can just take this image and push it into our generator and then have the generator output something else. Often this results in leveraging a different kind of architecture for our generator called a U-Net. What a U-Net does is it sort of, this is a different subject we can talk about more, but there's a lot of this in the literature. But a U-Net's really good for reconstruction. So actually, U-Nets came out of the semantic segmentation type of tasks, where I give you an image and I want to know what every single pixel in that image is. So this is a car or this is a tree. Or in the case of medical images, I want to know what's a tumor and what's not a tumor. But U-Nets, you can also do any kind of reconstruction in spatial. And so U-Nets leverage this thing called skip connections. So you have this sort of this encoder that takes an image input and breaks it down into sort of low resolution, high depth. And then you have this reconstruction decoder that goes from high depth back into spatial extents. But each one of these stages has an equivalent skip connection to the equivalent resolution on the other side from the decoder to the encoder. So units are very interesting, and they they lend themselves very, very well to these kinds of reconstruction tasks that involve spatial extents because you have this link between each layer at that same resolution. But now you can do some pretty amazing things. You can kind of see like the loss function for the pix-to-pix GAN is quite, it's the same. It's just BCE loss, but we've also now, because we have an output image and an expected image, right? We have to have these pairs. We have to have like, okay, I'm putting in this image of say we'll talk about like the black to white example, right? I'm giving you a black and white image, and I expect a color image, but that output could be a number of different things. So how do I tell it what it should be? Well, I should have the color equivalent image. So this is actually a supervised task because I'm giving it the black and white version of this color image. Then on the other side, I'm looking, well, does this look like the real data? But also, does this look like the target image that I'm expecting? Because otherwise, I can give you black and white of maybe a house, and you give me back a pink house, and it's supposed to be green. And so you need to have some kind of like paired images to train these things. But the results are quite striking. You can go literally from black and white to color. You can go from these input segmentation masks to these outputs. So you basically, now I can draw things like with just blocks of color, and I can get an image that looks photorealistic, right? I can go from satellite view to street view, right? I can go from daytime to nighttime. I can even go from sketches to actual images. And so this is a really cool sort of, I think, landmark paper that demonstrated this really fundamental idea of translating one image set of images to another set of images. So the next thing that kind of happened, well, what happens when you don't have those pairs of images, right? We talked about, well, in this case, I need to have data in my data set that goes from day to night. So that's easy enough. I take a picture during the day, I take a picture during the night, and now that's how I can make my data set. It's not that hard. But what if I want to turn zebras into horses? That doesn't exist. I don't have a zebra picture that looks just like a horse picture. How do I convert between those two? So CycleGAN came along and basically said, well, instead, if we want to do unpaired image translation, meaning basically go from one distribution of images to another distribution of images, but we don't have like a one-to-one correspondence between any one of those comparisons, we can use this idea of cycle consistency. And the concept of cycle consistency is quite intuitive. It's basically saying, well, if I have, let's use the horse-zebra analogy because it's so easy to see here. If I have a picture of a horse and I convert it into a picture of a zebra, and now I take that new picture, that fake picture of a zebra, and I convert it back into a picture of a horse, that fake picture of a horse and my original horse should be kind of the same. They should be relatively similar in their look. So we can literally just do an L1 reconstruction loss on that. We can do an L1 reconstruction loss on the opposite direction. We can also do an L1 reconstruction loss on an identity, right? So if I take my horse and I put it through my zebra to horse, then the output horse should be similar to my original horse, right? This identity function, and so on. We can also do just the general adversarial GAN thing, which actually in this case, right, because now I can look and say, well, this zebra image from horse to zebra, this zebra image should look like other zebra images. So I can just pass that image to a discriminator that looks at like just all pictures of zebras and tells me if it looks real or not. And in this case, actually, the CycleGAN used the MSC loss that we talked about earlier, and I think was one of the notable examples of diverging from the BCE loss early on. So CycleGAN's like a few years old now. It's like 2017 or 18, I believe. But it's quite striking. One moment, let me just take a moment to drink. Sorry, this has become a long lecture, so I had to hydrate. So yeah, the CycleGAN is quite amazing in what it can do. It can go from zebras to horses. It can go and do kind of like style transfer, so taking a photograph and turning it into a style of a painter that you like. The CycleGAN, I think, is one of the more interesting kind of creative GANs out there because you can kind of, I'm sure, think of many different ideas of unique filters that could be implemented with something like this. Um, so moving on, this is actually, I think I mentioned this earlier. This is one of the more, I think, notable and serious, I guess, applications of CycleGAN and GANs in general. So one of the kind of unique things that you can do with GANs is create data when you don't have it. Say the data is very expensive to accumulate, or it's very rare, or it's very dangerous to get. Like, for example, in this case, this is a paper out of Nature that used CycleGAN to take real images of CT scans and then convert them into images. Like, imagine what those images would look like if that CT scan had a tumor in it. So CT scans of people with tumors is very much a minority compared to CT scans of normal tissue. And so this allows you to generate this model that can go from healthy tissue to non-healthy tissue and back again. And now you can apply this to to the very, very ubiquitous healthy tissue data that we have. And now you can use that new data that you've generated using the GAN to train downstream tasks, such as a detector that can detect uh, you know, um, early signs of tumors and things like that. So this is, I think, a very kind of compelling use case for CycleGAN and for GANs in general, right? And just as a sort of banner, as a general banner for this, what we're really talking about here is taking understanding a real data distribution that maybe is scarce or limited, and then using that learned model to generate a lot of pseudo data that you can now use for downstream tasks such as segmentation or classification or whatever. So this is a very cool idea. Let's talk about kind of the negative sides a little bit. Adversarial attacks are kind of important to think about when it comes to machine learning, because it's been shown using sort of similar ideas to GANs that I can take an image, I can sort of figure out what I can add to it. I can add this sort of perturbation to this image and then plug it back into a machine learning model and trick it into thinking that it's something else, even though that image is imperceivably the same to a human being. So in this case, I could sort of take this image of a panda, add to it some of this adversarial perturbation, and then the machine learning model that my computer vision classifier is seeing something else. Now this seems like silly, like why would I ever want to turn a panda into a gibbon? But this has actually been done for like ID detection systems, so I can maybe look at a person and think they're somebody else. For example, like for key card entry systems that will look at a picture of me, and when they see me, they actually see like perhaps somebody with different security clearance and things and whatever. So this is an important thing to kind of be aware of, that machine learning models are relatively susceptible to these kinds of adversarial attacks. And so you can both use GANs to determine what these perturbations are, but you can also use GANs to prevent them, or adversarial training to prevent them. One approach is what's called virtual adversarial training. And the idea that, I'm not going to go too deep into the math because the math is always kind of confusing to me, but essentially what we're trying to do here is we're trying to minimize this divergence between the learned probability distribution of our model and the learned probability distribution of our model, but the input is perturbed by this random vector. And so the reason it's called virtual is because we're sort of randomly generating these perturbations, but you can see they're not super duper random. There is some math into how big should they be, what's the normalization, and that's what this is all about down here. But it kind of distills down into saying, well, I'm going to take an input to my model, and I'm going to get the output. I'm going to take that same input and then add some noise to it, and I'm going to run it through the model, and I want to minimize that divergence. I want to make sure that in both cases I'm getting the same answer. And so that's what this is essentially doing. And the reason that it's that adversarial thing is because we're kind of running essentially these two networks against each other, but one of them is a virtual network, right? One of them is actually our same network, but with a different kind of input. So moving on to kind of more unique, advanced stuff. We're kind of getting to the end of the lecture, I promise. But this is actually one of the more interesting, I think, subjects is unsupervised image-to-image translation. So we saw a little bit of this already in CycleGAN, where we don't have paired image translation. We just want to have go from one image domain to another. This approach is, to me, a very interesting one because the underlying intuition here is that given two images, right, the content of those images are invariant to the domain. So the fact that it's a cat and the fact that it's a tiger, that's information that is unique. It's not specific to that particular picture of a tiger or that specific picture of a cat, right? So in other words, those two images, these images of cats and tigers or whatever, share the latent space, and that's sort of what unsupervised image-image translation tries to do with UNIT, and it kind of combines a VAE with a GAN, and it's what's called a VAE GAN. And so the way that it works is you have a VAE that takes in an input, maps that to a latent by way of the way that VAEs work, right? Latent variable models, and that so decodes it into this, encodes it into this latent space, and then decodes it back into the image, right? Just like we've been doing with VAEs. And then that output is being given to a discriminator to determine if this image looks real or not. So if you're looking at this top, if you just kind of block out the bottom of this diagram in the top right corner, right, this E1 and G1 and D1, if you just don't think about the bottom side, it's basically a VAE, encode, decode, and then discriminate, right? And so this is sort of a basic VAE GAN. Now, the kind of unique thing about the unit is they actually train two VAE GANs sort of side by side, where the Z latent is shared. And the way they accomplish this is the last layers of the encoder are actually shared, so they're outputting into the same thing. And same thing in the last layer, the first layers of the generator. And so the first generator, the layers of the generator are also shared between the two. And so that way they can ensure that this Z latent is the same for both VAEs and for both discriminators as well. More detail on this in the paper if you're interested. But what's kind of cool about this now is I can take, I can use encoder 1 with generator 2 and a test time. So now I can actually put in an image, encode it into the latent space, now use that latent space encoding to generate an image from either class. And so that's sort of the idea of UNIT. Now, MUnit, multimodal unit, unsupervised image-to-image translation, kind of just takes it one step ahead, and you'll see a very similar idea here to StyleGAN. And basically what they're saying is, well, an image has this content that is domain invariant, so it's a cat or it's a dog or whatever, but it also has a style. And this style is domain specific. And so what we're going to do is we're going to split that image up into a style and into the content. The content, we're just going to do the same stuff we were doing up here, and then the style is going to be mapped by way of this mapping network, just like what we saw in StyleGAN. In fact, it's the exact same thing. It's adaptive instance normalization, which is then going to modulate our generator blocks, which is pretty cool. So the results are much better in the sense that now we can have sort of different picture, I can go from tiger to cat, but I can go to different cats because not all cats are the same, right? Whereas here, if I go with one latent, one generator, I'm going to have the same output image. Right here, I can actually have multimodal distributions on either side, which is quite cool. So this is a very, very promising approach. It's relatively new as well, and I definitely recommend you guys check it out. It's a very cool combination of VAEs and GANs, which we'll see again actually here with VGAN. We actually talked about this particular technique last lecture in the deep reinforcement learning lecture, which they use this idea for generative adversarial learning with Veil. And the big difference here is in the GAN loss, what we're also doing is we're trying to minimize this KL divergence in the encoder discriminator block. So this is very similar to InfoGAN, actually, in the idea that we're trying to maximize the mutual information between X and Z, the latent. And we're doing that by way of this sort of VAE KL divergence minimization. This is actually by very similar authors. This is by Peter Abiel, and so is Infogan. At least he was the last author on both papers. And so, this is quite cool. And I think this is actually really, really new. It's like 2020. I haven't tried it yet, but it seems very compelling to me that you get much better. You can see in the discriminator prediction graph over here, just these different ways that you can control the the bounds of the KL divergence by way of this IC value, which is cool. So, anyways, fun stuff and something to kind of be aware of. Finally, I wanted to talk about a couple of just like cool things that I'm excited about with GANs, and these are pretty new. So GAUGAN is just a UNet reconstruction network. They utilize adaptive instance normalization, just like we saw in StyleGAN and like we saw in MUnit. And they call it SPADE, so you can kind of see they have these SPADE layers, which is largely just adaptively instance normalizing it from this pixel segmentation image. And you can actually try this for yourself. You can go online and you can go on the NVIDIA webpage and draw like these landscapes using just paint, and that'll turn it into what looks like photorealistic images. And this is using, I believe, just image-to-image translation. This is very similar to Pix in architecture. In fact, you can see that it's Pix HD, which kind of adds more bottleneck layers or something like that, and adds this sort of adaptive normalization in there. So yeah, the specific architecture is a little bit more nuanced than just, hey, just throw a thing in there, but it's quite cool. I see I've given the wrong link here for the next slide, but just Google GAUGAN and you'll find this. More recently, this actually just came out last week or during GTC. This thing called GANcraft is just, I'm so excited. GANcraft sort of marries that exact same idea, GAUGAN SPADE, with what's called neural radiance fields, which if we have enough time, we'll have a lecture or two on neural radiance fields, which are very, very interesting. And what it's doing is it's combining neural radiance fields, which are actually learning implicit functions for a volumetric rendering technique, and it combines it with SPADE to then do image-to-image translation of like a Minecraft voxel world. And it's like really cool. I mean, look, like this does not look like a real image, but imagine playing Minecraft and the image is looking this good, right? And this is just upward mobility from here in terms of quality of this stuff. And what's really notable, by the way, about this technique is when you watch the video, you'll see that there's this very good coherence between each frame. So a lot of these image-to-image translation techniques are really cool in that they work on individual images, but as soon as you apply them to video, each frame of the video is like all over the place because it's this sort of stochastic thing, and so it's trying to not necessarily ensure that there's coherency between different images out of this sort of temporal sequence, but rather it's just trying to make sure that each image it's outputting is likely in context of this real data distribution that it's trying to replicate. And so this sort of like temporal coherence is something that's really hard to accomplish. Surprisingly, CycleGAN does a pretty good job of it because of the cycle consistency, and it kind of keeps things close to each other. Right? An image just slightly off is going to give you an image that's very, very similar, slightly off on the other side. But this isn't using CycleGAN. It's not involving any kind of cycle consistency. And actually, one thing I should add about MUnit and UNIT is that this sort of shared latent space does imply a general cycle consistency, which is why it's very interesting, is because when you have this sort of shared latent, you're ensured that you have this sort of consistency when you go from one to the other, and when you go backwards, it's going to have the same thing because we're still in that same Z space. But image-to-image translation generally does not have that property, and so this technique is able to accomplish that by way of actually, I don't really know. I need to read the paper, so I'm not going to pretend like I know exactly how they accomplish it. But one thing that's really possible is by way of the style encoder and also this neural rendering field that it's learning. So very fun one. It's a little bit late in the course to encourage anybody to do this as a project, but if you do this as a project, that'd be awesome. So yeah, like just to kind of cap it off, I've talked a lot about different things, but you can do stuff like what's called super sampling. You can take images that are low resolution and up-res them in a way that's more interesting or intelligent. You can go from input that's black and white to color. You can do this oldify thing. I'm sure everybody saw that sort of app that came out maybe it was like a year ago at this point, where you give it a picture of yourself and it'll show you what you would look like if you were old or young or in between. And so there's a lot of very interesting applications of GANs. We're just scratching the surface. It's still actually a relatively early technique. It was only invented 8 years ago or 7 years ago. So it's a very, very fun thing to play with, and definitely I think one of the more interesting ideas in unsupervised learning in general. So yeah, that's it for this lecture. I know I said we're going to talk about transformers next lecture, but we'll actually talk about transformers next lecture. And hope I'll see you. I'll see you then. Bye.